Hey everyone, we are going to revisit Riemann sums in lesson 43. Now that we've used Riemann sums with finite number of left, right, midpoint rectangles, and we've also used this with trapezoids to approximate area under a curve, we're going to now extend this concept and finding the exact area by looking at n number of rectangles and calculating the sum of the area of those rectangles as n approaches infinity. All right, and so you remember me talking about n number of rectangles as n approaches infinity will give us a more accurate area. The more rectangles we have, the more accurate our area is. All right. Okay, so first thing that I want to talk about is that obviously we can see here that this is the definite integral. And when we see something like this would just represent like the height times the base. This represents like a rectangle. Okay, so basically we have these rectangles from A to B, and that's that area underneath the curve from A to B. All right, that's what we're seeing here. Okay, so when we see something like this here on the right side of the equation, we're talking about a Riemann sum. All right, and then this notation looks kind of funky, right? This is a summation symbol, and you may have seen that before. Remember, as n approaches infinity, we're going to use the same concept of number of rectangles, right? Well, that means height times base, right? Or base times height. So, we get the height of the rectangle by this, x of I that we see here, all right? It's a little subscript, but basically this is the notation that we might see on the AP exam. And so what is this height? What does that represent? Okay, I'm just going to write here height. And that's this formula that we see here, okay? This is the formula for height of the rectangle, all right? And then over here, you can see that we have the base. All right, well, how do we get the formula for the base? And you might remember that we did this with Riemann sums, right? And the formula for the base is just b minus a over n, all right? And then that's what we'll see there, okay? I'm just gonna write here base, so base times height. That's how we get to that Riemann sum. All right, so let's take a look at some examples, all right? Rewrite using the definition of a Riemann sum. And what that means is basically just to use summation notation or like sigma notation. Ultimately, that means that we want to write this as the limit as n approaches infinity. All right, you'll see I have that over here. Okay, and then we have this summation notation. We've got our n up here from I equals 1, okay? And then we write here f of x of I, and then times the base here, which is delta x, all right? Okay, so now we need to plug in our particulars, right? Well, do we know how to find this base, right? Isn't that just b minus a over n? Yeah, right? Okay, well, do we know what b minus a over n is? I mean, we know what b and a is, right? Isn't that just going to give us 5 minus 2? And since we really don't know n, we can just leave it like that. Anyway, 5 minus 2 is 3. This gives us 3 over n. This is the base right there, okay? All right, let's circle that so we don't lose it in our work. And then we want to find the height of the rectangle now. So we got our base. We're looking for the height, okay? All right, well, how do we find the height? Well, that's this other formula, right? This x y. Okay, so isn't that just a plus I times that delta x, right? Remember, delta x, we just found it to be 3 over n. And a, I believe that was given to us in our definite integral, right? Remember, this is the integral from a to b. So we know what a is. A is 2. And we know that delta x is 3 over n. So that means we're going to get 3 over n I. That's going to give us the height of the rectangle there, okay? All right, but what happens when I plug it into the f function? Well, the f function is x cubed. So I plug that into the f function. I'm basically going to be getting here 2 plus 3 over n I. Oops, I forgot my I, right? That's x, now to the power of 3. There we go. All right, so that's what we have here. Now, let's write this in summation notation. All right, so this is going to become here the limit as n approaches infinity. We're still going to go from 1 to n, right? N number of rectangles as n approaches infinity. I'm just going to plug in this piece right here, which we just found to be this 2 plus 3 over ni cubed. And then times the delta x, which we know now is 3 over n. There you go. That's all we got to do here. That would be our answer on how we would rewrite this as a definition of a Riemann sum. Okay. All right, let's take a look at another example. This one is 4x, right? Definite integral from 4x from 3 to 7. So kind of the same thing here, right? Let's start by finding the base, delta x, right? Okay, so we know that that's b minus a over n. And that's going to give us 4 over n. Then we want to go ahead and find the height of that rectangle, right? Okay, well, that's going to give me, let's see, 3, that's the a value, plus then delta x times I. Oh, that's just going to give me 4 over n times I. Bingo. Now, if I take this and plug it into my f function, right, which is this thing here, plug it into my function, I'm going to get 4 times this 3 plus 4 over n I right there. Okay. All right. So now I'm ready to rewrite it as a definition of a Riemann sum, which basically means just the summation notation. All right. So let's go ahead and write limit as n approaches infinity. We write our summation notation. We go from 1 to n as n approaches infinity, remember. Okay. So we got this first part already, right? That's just this 4 times 3 plus 4 over ni times the base, which we said was 4 over n. And that's all it is, all right? Nice and easy, writing it as a definition of a Riemann sum. Perfect. Now, can we go backwards? If you have that definition of a Riemann sum, can we go backwards and write it as a definite integral? What information can we take away from this question? Well, I know that this formula, b minus a over n, this is always going to give me the base, right? That's what I know. So maybe I'll start with that. Do we know what the base is? It should be this, right? 3 over n. Okay, so let's start by saying that b minus a over n is equals to 3 over n. Okay, now do you know anything about b or do you know anything about a? Right? Now, remember that when we did the whole height thing, right, x of I here, that always told us like a plus, delta xi. So we should have an idea that a is 2, right? Just because I see it right there. So that tells me that a is 2. With that being said, I can go ahead and set this up as b minus 2 over n, which is equals to 3 over n. And I guess we could have gotten rid of the n's by multiplying n on both sides, right? It's just to kind of find out your a's and your b's, because we want to write this as an integral now, this way. Okay, that's our goal, right? Add 2 to both sides, and you end up finding out that b is equals to 5. Okay, with that being said, I can already kind of start off by saying, hey, this is the integral that goes from 2 to 5, right? I just got to find out what function this is. Well, if I know that that's a, and I already know that delta x was 3 over n, right? Here's my delta x I, right? There you go. And then, of course, this is delta x. Didn't we just plug in x of I? That means that our function is just going to be tangent of x, all right? So we're going to go ahead and write here that this is just tangent of x. Remember, very, very, very careful. Don't forget about the x, all right? So anytime you set up an integral, you always want to write dx. All right, so here's how we rewrite it using a definite integral, all right? So overall, not so bad. You kind of have to find a on this, and you have to find b, and just kind of working backwards. All right, let's do a few more. I think these are a little harder. All right, here's this question, another trig function, right? So we can see, a couple things that you can take away, probably like, oh, that's screaming at me, right? Maybe you already know that a is 5. Perfect. But what is delta x? Should be right here, right? 3 over n. Okay, and remember that delta x is always going to be that b minus a over n. So if you plug in your a value, which is, well, 5, right? we get b minus 5 over n, right? Remember, if we multiply n on both sides, we can get rid of that. And so we end up with this. And then now we just add 5 to both sides. So we find out that b is equals to 8. And this is a lot of information, right? Because I can see here that this is a sine function that's plugging in that a plus delta x. That already tells me everything I need. This is sine of x. So here we go. This is the definite integral from a to b, which is 5 to 8 respectively, right? And then my function is just sine of x dx. Be careful, don't forget about your dx, all right? Okay, these questions do come out on your AP exam. You can expect them to be non-calculator MCQs, all right? Okay, let's see. Let's do another one. Here we go. We got this monster going here, and look at that. That's screaming at me, and that is my delta x right there, okay? Also screaming at me is this thing here, and I already know that that is a, okay? Because this is some function, and this is what's getting plugged into it. I can see this thing here in front of the I, which means that's delta xi, right? And that's the same value, all right? So be very careful with that. Let's set this up, right? We got delta x, which is equals to, of course, b minus a over n. Now we know that a is 1, okay? I'm gonna plug that in, but also I know that delta x is this thing, which is e minus 1 over n. And I already know that a is 1, so I'm going to say b minus 1 over n. Remember, if we multiply n on both sides, that goes away, and we end up with e minus 1, which is equals to b minus 1. Okay, let's add 1 on both sides. Adding 1 over here gives us e plus 0, which means b is equals to e. Okay, that's kind of weird, isn't it? Yeah. Now, when we write our integral and we go from a to b, that's going from 1 to e. That looks weird, but keep in mind what e is. Back in pre-cal, you should have learned that e was about 2.72. All right, so that makes sense. This is a lower limit and an upper limit, so I'm not going to think too hard about that. Now, I can see here that this is a natural log of something. I can see this is getting plugged in, which means the function that we're seeing here is natural log of x. One thing missing here, dx. Be very careful. I keep saying it, right? Don't forget about your dx. I hope that helps everybody. That wraps up lesson 43. And you're going to do the assignment that I post for you, okay?